Hi, so today we're looking at another problem on statistical physics, and well, what we have today is, well, some gas with volume V, number of particles, N, and energy E. In this case, we have that the volume is fixed, right? Our gas is in some kind of box, as is usual in these kind of problems. And this box, it doesn't have to be rectangular, we don't really care about the shape of the box, but it has some fixed volume V. And our gas is inside it. So volume V, energy E, the energy is also constant, it doesn't exchange energy with the medium, and the number of particles is constant, okay, the box is sealed. But there's a peculiarity in this box. We are used to working with three-dimensional boxes, right, like the ones that we see every day. But in this case, we have a D-dimensional box. So we're trying to work in a more general situation, where D can be 1, 2, 3, or even higher dimensions that we can't really visualize. Apart from this, we know that the particles are classical, non-relativistic. And what is meant by this is that the kinetic energy is given by our usual expression of 1/2 mv squared, which can be rewritten in terms of the momentum of each particle. Okay, so for each particle, we will have this. But we will assume that all the particles have the same mass, so this will be our kinetic energy. And our potential energy will just be the box potential for each particle, and this just makes sure that all the particles are inside the box. So, let me just write it. So if we call the region of space that we consider our box coarse V, this is contained in a d-dimensional space. Okay. Usually we have R3 because we're working with 3 dimensions, but in a d-dimensional space, well, this is just a subset of the d-dimensional real space. And this potential just says that, well, if the position of the particle is inside this box, it is 0, it doesn't really contribute to anything, but if it is outside, it is infinite, meaning that it cannot be outside, okay? We don't have particles outside the box. So, let me just write this here. So, our potential energy is just given by the momentum of each particle. Yeah, we can write this as the modulus squared over 2m. And the potential just tells us that we are inside the box, so we don't really have to write. And now, before we get on to solving the problem, let's explain a bit about the canonical ensemble. In this case, after we're going to be doing an overview and not getting into too much detail, it is worth spending some time on the phase space of the position, because it changes a bit from our usual ideal gas considerations. So, well, of course, this is an ideal gas, I didn't say it, but we assume that it behaves as an ideal gas. So this gamma just tells us, the top gamma tells us that it is the phase space, which is the set of points, or the set of states that are possible for a system, and a state is given by Qp, which just gives the position. Q is shorthand for the position of each particle. And P is the momentum of all the particles too. So these are shorthand notations for the position for the particles and the momentum of all the particles. But usually, well, this is just the position of particle 1. In general, the position of particle I is given by the first component of the ith particle, the second component of the ith particle, and the third component. But in this case, we are in a d-dimensional space, so we don't need 3 coordinates to specify the position of a particle, but rather we need d. So each vector has d components. Okay? So what we will have is that our phase space is composed of d times n dimensions. And yeah, well, 2d n dimensions. D n dimensions for gamma q. Okay, we have n particles, but we also have d components, so dn dimensions for gamma q, and dn dimensions for gamma p. Now, if we go on to the volume of a phase space, which is denoted by this phi, which is the fundamental quantity in the microcanonical ensemble, we have that we are assuming undistinguishable particles, so we have to include Gibbs factor to not count particles more than one time, and we include it by putting a 1 over n factorial. This is Planck's constant, and we know that Planck's constant is raised to number of degrees of freedom of our system, and the degrees of freedom can be thought of as the number of coordinates that we need to specify the position of the particles. For one particle, we have d degrees of freedom, we have d coordinates, but given the fact that we have n particles, we need d times n coordinates in order to specify the positions of all the particles. So our Planck's constant factor will be raised to the dn power. In the case of 3 dimensions, d is 3, and we get our usual h to the 3n, h to the 3n. And this integral is just the same as always. This is the Heaviside step function. It is 1 when the argument is greater than 0, and 0 when it is less than 0. And our dp and dq's are just shorthand for our bigger differentials. So dq is just dq1, so on, dqn, and in turn dqi is just shorthand notation for this. For the first component, second component, and the d component of our ith particle. So really what we have here is, let me just write it in terms of products because they are a lot of terms. So what we have is n times d differentials. Okay, as we said, it's the same number as our degrees of freedom. So what this differential means is just that we are taking the product of the components of each particle. Okay, so for each particle we have that the differential is given by this. So for any kth particle we will have this. So this is a product of d terms, but we're multiplying this n times, so we get our n d terms. It is usually it can be written the integral instead of this notation. We can use the product notation for both the differential in Q and the differential in P. So likewise, the differential in P is just dp1 and so on up to dpn, and this can be expressed in terms of productorial as the product going from 1 to n of the differential of the components of the momentum. D, okay, and as you see, it is a lot of notation. Okay, we have to write a lot of things, so it is a lot easier to just stick with dq and dp. And this is what we will in fact be doing. I just wanted to mention it so you don't get confused with the notation and know exactly what everything is. Now, the objective of the microcanonical ensemble is, of course, to find the volume of the phase space, this phi, but we want to find this volume in order to find the entropy, from which we can find all the other quantities like the pressure, the temperature, and the heat capacities, as well as the ratio between the heat capacities. So, this is our usual expression. There are other expressions, but this is the one that we will be sticking with because we're gonna use the volume of the phase space. And what else? Yeah, we need the Stirling's approximation. Okay, this is called Stirling's approximation, and it just tells us that when we have a really large number n, when n is a natural number, the lateral log of its factorial is approximately given by n log n minus n. And a generalization of this result which we will be proving in another video. Okay, we will be making a lot of videos on all of these results, but separately. So we'll make a video on the student's approximation for regular n and for the gamma function. Okay, so what we know is that the gamma function of some complex number is not some complex number of n is n minus 1 factorial. Okay, so this just extends our notion of factorial, but this only holds for the values that for which n minus 1 has a defined factorial. Nevertheless, this can be extended to any complex number with the condition that its real part is greater than 0. And also by analytic continuation, you can extend it to the whole plane except for negative integer values, and I think non-integer values. But we'll talk about that in another video. So if we have the gamma function of some complex number with the condition that its real part is greater than 0 and its modulus is a lot greater than 1, what we mean by this is that, well, this condition is similar to this one, but instead of having a natural number, we have some complex number. So this is a kind of the generalization. And well, the argument of C has to be less than pi minus some arbitrarily small constant. And this just means that we are in the first revolution around the complex plane. And what else? Yeah, I think that's it. So this will be our expression for a Stirling approximation, and the volume of the, and there's another result that we'll need is the volume of an n-dimensional sphere, and it's given by this expression. We will also prove it in another video. And this gamma right here is in fact the gamma function. I'm not going to write the definition of the gamma function because really we will not need it. We will only need this relation right here, that the gamma function of z plus 1 is equal to this. And this holds if, of course, c plus 1 and c are such that the gamma function of them exists. And what else? Well, these are just some thermodynamic relations. If you want proofs on them or an explanation of how to get to them, just check out the thermodynamics course that we will be making. So well, let's just get started with the problem. The first thing that we need to know is the phase space of our system. And we know that the phase space of our system is, well, P has no restrictions, so the momentum can have any value, but Q has the restrictions to be constrained to a d-dimensional box. So well, that's it. So let's just write the volume of the phase space. This is given by 1 over n factorial h to the number of degrees of freedom, which we said is d times n. Now, we will split this gamma into the phase space of the momentum and of the position. So this is the phase space of the momentum, and this is the phase space of the position. And here we have E minus h dq dp. But what is our Hamiltonian? Well, our Hamiltonian is just expresses the energy of our system. Let me write it right here. So our Hamiltonian, it is the sum of the energies of each particle. Because we have no potential energy, all we care about is the kinetic energy that we talked about. So we can write the momentum square of each particle over 2m. And I write 2m instead of 2mi because we assume that all the particles have the same mass. And yeah, so what is our Heaviside step function? Our Heaviside step function is 1 when E minus this sum, which is our Hamiltonian, is greater than 0. And 0 when E minus h, okay, this is just h, remember, is less than 0. So we can rewrite this expression by considering that E is not 0. So then this inequality by dividing by E just becomes 1 minus 1 over E and this sum. Now, because E is constant, it doesn't depend on I, on the particle, we can take it inside of the sum and we end up with this. So this is our condition, okay? This is the function that we're integrating. If this doesn't hold, then the integral really is just 0 and the volume of our first space is just 0. So let's just rewrite this, okay? So just remember that we are in this phase space, but here P, okay, all the values of P satisfy that 1 minus this sum is greater or equal than 0. Okay? So, yeah, that's it. So let's just rewrite this integral. Before we do that, notice that the Heaviside step function does not depend on the position, right? Yeah, because our momentum, as we said before, sorry, our Hamiltonian only depends on the momentum. So we can actually take this out of the position integral and get 1 over n factorial h to the dn, the integral over p, and I'll expand the Heaviside function later, minus h, and then we have to do the integral over q dp. Now, the integral over q, this region right here is the region that all the q's can occupy, and this region is the volume of the position phase space. So this, it is the integral, well, let me just write it like this, over v. Okay, this is gamma. Okay, gamma q is just v times v. This just means that our first particle is in the volume v, the second particle is in the volume v, and so on. Yeah, so our general dq, our general q, is in this space, because the particle cannot be outside the box. So this is our expression. And now, what is the integral? Sorry. Sorry, it's an n. So we have an n here because we have n particles. Now d. Sorry about that. So what is the integral? The first integral, it is just the volume of our box. The second one is just the volume of our box again, and so on, so on, so on. So what we get is v raised to the nth power. Okay? Because that is the volume that all the particles can occupy. Each particle can occupy a volume of v, and we have n particles, so we have this. So we can rewrite this in terms of the volume. Because the volume is constant, it can go out of the integral of the momentum, and we end up with this. Now all we have to do is to calculate this integral. And as we said, this region right here, this region is the set of points P belonging to the real numbers, but in which dimensions? In dn dimensions. And why dn dimensions? Because P is set of points q1, let me just put it like this, q1, so on, pun, this should be a p, p1 and so on. So there are n coordinates, but we also need d coordinates for each momentum, so we have dn coordinates. So any point P has got dn coordinates, and we are in the dn real space. But we have the restriction that this has to hold, because otherwise the Heaviside step function is just 0. So we have the restriction that 1 minus this sum is greater or equal than 0. And this doesn't really tell us much. So what we'll do is we will make a change of variables. And let me just call this new variable u, and I will call ui equals to, oh sorry, and this should be n, equals to 1 over the square root of 2me pi. So this is our change of variables. And why are we doing this change of variables? Isn't it a bit arbitrary? Well, not really, because if we take the modulus squared, we will get the same. So what we're looking for is that we end up here with just u squared. So everything is easier. So if we take the modulus, in fact, if we do this and take the modulus squared, we get 1 over 2m e pi squared. Now, okay, we have our new inequality, but we don't have our differentials. So what is let's just say du? Well, dui, its definition is that it is the first component of the ith particle times the second component of the ith particle, and so on until the d component of this ith particle. But what is each differential? Well, when we define this, we can rewrite this change of variables in terms of the components. So we will have the first component of ith variable, the second component of the ith variable, of the ith particle, and so on, until the d component. And this is equal to 1 over the square root of 2me of each component of our particle. So let me just write it like this: 1 over the square root of 2me p1i, and so on, like this. So this is what we have. If we take differentials on both sides, we will see that du1 is equal to 1 over the square root of 2 me dp1i, and so on. So what we will have is that there is a factor 1 over square root of 2 me raised to the div power. And why to the div power? Because we are multiplying 1, 2, 3, and so on up to dpd. So this will be dp1 of ith particle, dp2 of ith particle, and so on until we get to the d component of the ith particle. So this is our new differential. Well, by definition, this is just dp. So what do we have? We have our change of variables, we have our new inequality, and we have our new differential. So we are actually ready to compute this integral. So let me just write this here, and just remember that dp, if we take this factor to the other side, it is just well, the dpi, sorry, let me just write it like this. It is just the square root of 2 me raised to the div power dui, and that ui squared is equal to 1 over 2me pi squared. So, and remember that this is the condition that we want. So our region will have to satisfy this condition. So let me just erase this for a minute and you'll see what I mean. So we can rewrite this as, well, v to the n power n factorial h to the 3n times the integral over the space of the momenta, but the space of the momenta in this case is going to be, it is going to be 1 minus the sum going from 1 to n of u squared. Greater or equal than 0. Okay, so this is the condition that has to hold. And if this holds, we have 1. If this doesn't hold, we have 0. So this is the condition that the phase space has to satisfy. If it holds, the Heaviside step function is 1, and if it doesn't hold, it is 0. And our differential, well, we know that it is dp1 times so on, so on, so on, until we get to the nth particle, dpn. Let's look. So, well, we have this. We just need to express it this 2me raised to the fifth power of du1, and we also get another factor here to the fifth power dun. So as you see, we have n factors of this. Okay, so because there are n particles in differential, we have the square root of 2me raised to the fifth power, but this n times, so it is just raised to the nth power. So if I just erase this, which I think it's already understood, we get b raised to the nth power n factorial h to the dn. I'm sorry, I wrote a 3 here, it should be a d, because we're in d dimensions, and this factor 2me raised to the dn power, okay, was raised to the fifth power, but we have n terms. And now notice that this condition that has to hold can be expressed as this sum being less or equal than 1. Okay, we just put it to the other side. So we have this sum being less or equal than 1, and we have 1 du1 and so on dun. And notice that whenever we have a multivariable integral and we are integrating the function 1, we are integrating the volume of the space in which our variable is moving. That is, we're integrating over this space, and this just means that we're calculating the volume of the space, of the subspace of the subset, sorry, of gamma p, such that this holds. We know that this is the expression of the inside of a sphere. Okay, this is the volume of a sphere in how many dimensions? Well, in dn dimensions. Why dn dimensions? Because our gamma p space has dn dimensions. As we said, they are the coordinates needed to specify one point in this space. So this is the volume of a dn dimensional sphere. And if you still have doubts about this, I will be making some more videos explaining this kind of integrals more in depth. But just remember that the integral over some region and some variable u is just the volume of the region. Okay? So that's it. In our case, we know what the volume of an n-dimensional sphere is, and in our case, n is equal to dn. Okay? So we have b to the nth power n factorial h dn square root of 2 me raised to the dnth power times, well, pi raised to the dn over 2 raised to the dnth power over 2, the radius raised to the nth power, dn in our case, and gamma of dn over 2 plus 1. And I just want you to notice one thing. This represents a sphere of radius 1. The inside of a sphere, the volume of a sphere of radius 1. So the radius in our case is just 1. So well, this is just 1. Okay, so I decided to rewrite our result here, the volume of our phase space. But before we continue, let's check if the dimensionality is correct. This is something that we should always try to do when we are dealing with some physics problems, in order to at least check if our result makes sense. So, well, we know that the volume of our phase space is dimensionless. And why is it dimensionless? Because we have introduced this h factor here. And that h factor there, its only purpose, or one of its main purposes, is to make the volume of a phase space dimensionless. So, well, let's see if it is in fact dimensionless. In order to do this, I want you to go back a few steps. If you go back in the video, you'll see that at some point we said that the volume of our phase space was Vn over n factorial h dn and times the integral over the phase space of our momentum. And what is the dimensions of this? Well, these dimensions really, because the Heaviside function doesn't have dimensions, this, if we write these brackets, this has the dimensions of dp. But these dp are n differentials. So this really is the dimensions of dp1 and so on, dpn. But notice that each dp has n p's in themselves. D. So here we have dn dp's. Okay? So as we commented, there are d times n differentials. So really, this is the dimensions of momentum, but times raised to the dnth power. Okay? So these would be the dimensions of momentum, but all of these raised to the dnth power because we have dn momentum multiplying each other. Okay? Another way of seeing this is, well, right here we have, after we solve making the change of variables, our integral, we have this part right here, which does have dimensions, right? Mass times energy has dimensions. Pi and gamma function don't have dimensions. And you could argue that 1 should have dimensions of length because it is the radius of the volume for phase space. But in this case, it doesn't, because it doesn't matter if it is a volume or whatever, it doesn't have to have dimensions of length. For example, here, if gamma of p was a sphere, the dimensions of the radius of the sphere wouldn't be in meters, it would be in the units of momentum. So here, the radius, in this case 1, okay, 1, u was, this was the radius of our sphere, has the dimensions of u. And what are the dimensions of u? Well, the dimensions of u are given by this change of variable right here. So the dimensions of u, which will be the radius of our sphere in our new u phase space. I'm sorry, it might be a bit confusing with all these change of variables and things, but if you go back a few steps and try to look for the dimensionality of this volume in the phase space, you will see that all of this adds up. Okay, so well, the dimensions of u are, well, they are the dimensions of momentum over the dimensions of mass times energy raised to the 1/2 power. But what are the dimensions of energy? Well, we know that energy can be expressed, at least kinetic energy, as this. So these are kilograms times meters squared over seconds squared. So all of this right here, well, instead of doing this, let's just do it by component. Okay, this holds for example uxi and pxi or pyi and so on and so on. Just go back to the change of variables and you see that it makes sense and that it is applied to each component. So well, these are the dimensions of momentum. And what is momentum? It is mass times velocity. So it is kilograms times meters over second, okay? And all of this times the dimensions of mass times energy. Well, if we put an m here, we have to get another kilograms. So here we have kilograms squared, but we're taking the square root. So this cancels out and this cancels out, and this is dimensionless. So if U is dimensionless, the radius in this phase space is dimensionless, which is 1. And so we'll have only, in this part, the dimensionality only corresponds to ME. But what is the dimensionality of ME? Well, we have it right here. It is this one. But this, if we just write dimensionality of momentum, is just the dimensionality of momentum squared. Okay? But the dimensionality of momentum squared, and we're taking the square root, well, we have here the dimensions of momentum raised to the dn. Okay? So all of this, after all this argument, let's use this one. After this kind of long argument, we get that the dimensionality of all this is just the dimensions of momentum, but raised to the dnth power. Okay? So is phi dimensionless? Well, let's just check. The dimensionality of phi is, well, the dimensionality of the volume. Well, the volume is usually given in meters cubed, but we are dealing with a d-dimensional space. So volume is given by meters to the dth power. Okay, if we were in 3 dimensions, this d would just be a 3. Over n factorial doesn't have dimensions, but Planck's constant does have dimensions. Let me just remind you that it has dimensions of action, which is joules times second, energy times time. So here we have joules times second to the dnth power. And here we don't even really need to go back to the momentum, because we can express it as 1/2, or let me just put it like dn halves of kilograms times joule, because this is mass times the energy. Okay, or you could express it in terms of the momentum, which here we just have to change some things, but well, let's just do it like this because we have joules and joules. So here we have n dnth power times kilograms to the dnth over 2 power. Well, joules and joules cancel out, and we get joules to the dnth half power times second to the dnth power. But what are joules in the SI unit system? So, well, joules is equal to, well, if you don't remember, you can just say that, as before, the energy is given by 1/2 times the mass times velocity squared. And this is just kilograms times meters over second squared. Okay, so joules in the SI system is just this. So if we put this here, we get, let's just write it like this. 1 over joules to the dnth over 2 power times, and let's just raise all of this to the dnth over 2 power 2. So here we just get kilograms, and here we get meters squared and second squared, and here we get kilograms times meters squared over second squared. So as you see, we get that these two terms cancel out because they are raised to the same power, and thus this is dimensionless. Well, yeah. So let's just get on with the next part of the problem. So at least if we don't know exactly, we don't know exactly if our answer is correct, but what we do know is that the dimensionality is correct, and well, so far that will give us a hint that we are doing things right. Now the entropy. So this is the key quantity I want to calculate. So let's just do it by one of its definitions. The definition what I'm using is just the one using the expression of the volume of our phase space phi. So this will be just the natural log of all of that. But before we get into that, let's just remember some properties of logs. Okay, product becomes a sum, division becomes subtraction, and raising something to some power is the same as multiplying by the natural log. So with these properties and some approximations, we're going to get a really nice expression for the entropy. So, well, you can do it more calmly at home, but I'm going to try to do it faster because the video is already a bit long. So I'll explain every step, but I just want to write things as fast as I can. So the volume raised to the nth power is multiplying, so we can take the natural log of Bn, but this n is raised to some power, so we can take it out here. So we got rid of the volume, minus, because n factorial is dividing. And let me just put some big brackets here. The natural log of n factorial, and you see why I put these brackets, because it's dividing, minus, and here I'm just going to take out the n instead of the dn. So I'm going to put an n here, h to the d, and now 2m pi e, so we get 2m pi e, and again I'm just going to take out this n and raise all of this to the d-halves power, minus, let me just write it here, minus the natural log of dn over 2, because it is dividing, minus, and then I'm going to put another bracket here, the natural log of gamma, of dn over 2. A lot of brackets are coming into play, but well. Okay, so these are the, if you want to show how it got from here to here, just try to apply these rules by yourself and see if you get to the same expression. Now, what we're going to be doing is we're going to be applying Stirling's approximation for the factorial and for the gamma function. First of all, for the factorial, we have that n is greater, a lot greater than 1. Okay, we have this. We can apply this expression. And this equal sign will become an approximate sign. And this expression right here, this limit, is called the thermodynamic limit, in which we are considering a really high number of particles. And this is what we usually do in statistical physics. We do some theory, some background and definitions. We calculate the entropy, and then we go on to the thermodynamic limit to try to reproduce our thermodynamic properties. So if we have this ln factorial becomes n, natural log of n, minus n. Of course, remember that we are putting an approximate sign, but given that n is so high, so big, it's almost an equal sign, okay? But well. Now, we can do the same for the gamma function, although we have some restrictions. This is also Stirling's approximation for the gamma function, but it only works under these 3 restrictions. The real part of c, which is in general a complex number, is greater than 0. In our case, c is dn over 2, and well, d is greater than 0, because we are assuming that the dimensions of our box are at least 1, 2, 3, or so on. N is greater than 0, because we're assuming that we have at least more than 1 particle, and 2 is greater than 0, so this holds. If we take the modulus, well, because it is a real number, this modulus is a real positive number, this modulus is just dn over 2, and this is a lot greater than 1 because n is a lot greater than 1, okay, and d is not, it's a positive integer, so this holds. What else? Well, we have that the argument of c is less than pi minus some epsilon, some arbitrarily small epsilon. And this is actually true because c belongs to real numbers, so the argument really is 0 or pi. And in this case, it is 0 because we are dealing with this part of the complex plane. Okay, I'm sorry for my bad drawings, but we're dealing with this part of the complex plane. And this part, the angle, the argument of all these numbers is just 0. Okay. If we had a negative number, well, we would be dealing with some pi here, and we'll have some conflict with branches. But we're not dealing with that. And yeah, so that's it. We're dealing with this branch right here, so with this set of numbers which have argument 0. Well, then the absolute value of the argument is 0. So yeah, I think we are in conditions of applying our gamma function approximation, or Stirling gamma function approximation, and let's just do it. So instead of the natural log of this, we will have the natural log of the square root of 2 pi over c, but c is just dn over 2, so dn over 2, but these 2 can go on top, and we have this, times, and we can actually just partition it into a sum of logs, because we are multiplying, and we get c to the c, c to the c minus the natural log of e to the c. And I'll just substitute the c afterwards, but for now we can just take this c in front, put this c here, we can put this c in front, but the natural log of e is just 1, so we get minus c, and yes. Now, c is just dn over 2, but we can factor out this c, so let me just, c is just dn over 2, natural log of dn over 2 minus dn over 2. Okay, so now, what I'm going to be doing is I'm going to take out an n out of all these terms. Well, all of these terms have an n, so there's going to be no problem. But here, these two terms do not have an n. Let me just put this brackets. Do not have an n, so we're going to have to divide by 1 over n. Before we do that, let's just group all the terms together, okay? So, kbn, and well, this term can go with this term, and we could get v minus, just dividing by n, so we're getting rid of this, minus h to the d, h to the dth power, times 2m pi e, okay, 2m pi e to the d half power, and really we can rewrite all of this as raised to the d half power if we just put h squared. So we're getting rid of those terms. Well, of course, we have this term right here, which we have not dealt with. We just put it as a plus 1. And, well, we have another n here. So we can put this dn over 2 right here, raise it. So this would become n times natural log of dn over 2 raised to the d half. And this would be dividing because we have a minus sign. So we have to divide by 1 over, we have to divide by, 1 over dn over 2 and raised to d half power. We'll simplify this afterwards. Let's not forget the one that we just erased. And, well, of course, we have this one, but if we have this minus sign with this minus sign, we have a plus d over 2, okay? And lastly, we get minus the natural log of dn over 2 minus the natural log of the square root of 4 pi over dn. But remember, we have taken out an n out of all these terms, and all the terms had an n except these two last terms. So here, we have to write a 1 over n. And this is it. So this is our expression. We can simplify it a bit. We can say that, well, this is raised to the d half power, so dn over 2, the 2 comes on top, this becomes a 4, and this dn over 2 just comes here dividing. Sorry, this is just dn h squared, and that's it. Now, if we add these two, well, we can just leave it like that. That's 1 plus d over 2. Just plus 1 plus d over 2 minus, we can put this together and well, we know that dn over the square root of dn is just the square root of dn. So all of this just because, well, of course this 4 comes like a 2 and this 2 comes out. So, well, let me just, okay, so, yeah, this, and, oh yeah, sorry, this is a plus sign. I know something was wrong here. This will have minus sign, the minus comes here, it factors out of both terms, and we get the natural log of square root, and what is, I think I remember, natural log of, the 2 cancels out, and we get the square root of dn pi. dn pi. Okay, let me just check. 2 comes out. Yeah, that's it. So now we can actually get rid of this term if we consider that n is a lot greater than 1. This is the same as taking the limit as n approaches infinity. So let me just say that the limit when n approaches positive infinity of 1 over n of the natural log of this, well, this is infinity over infinity, so we can apply, in this case we can apply L'Hopital's rule, which is differentiating on top and the bottom. We differentiate on the bottom, we get a 1. If we differentiate on top, we get the following. We get, well, before we can differentiate, it might be a lot easier if we just put this square root as a 1/2 here. So here we will have a 1/2, and now we can differentiate much easier. And well, the derivative with respect to n here is just d pi, and over here we get dn pi. So this is 0. So as n becomes a lot greater than 1, this goes to 0. So this would be the expression of our entropy. Let me just write it up here, and we'll check the dimensionality, if it is extensive, and if the argument of the natural log is dimensionless. So let's just check this. So the entropy, let me just write it in terms of V, N, and E. Okay, it's given in terms of EVN, and it is KV, Boltzmann constant, times number of particles times the natural log of this expression, natural log of B over N over 4 pi ME, 4 pi ME, D over 2, and on the bottom we have dnh squared, dnh squared, I think. And what else? Yeah. Plus 1 plus d over 2. So this would be the expression of our entropy. Let's just check if it is I copied correct. Yeah, so that's it. Now, now things should be much easier. Okay, we have getting these longer parts out of the way, but the rest should be easier. Really, once we have the entropy, we have actually almost solved the problem, because there's really not much else that we have to do. So the dimensionality, well, the dimensions of the entropy should be the same dimensions as Boltzmann's constant, and well, n has no dimensions, 1 has no dimensions, d has no dimensions, and the natural log has no dimensions, so dimensionality is correct. The extensive property, well, if we replace n by by a lambda, b by a lambda, and e by a lambda e, we get that So what I'm saying is that if we consider this, well, we would get lambda and lambda cancel out, lambda E and lambda N cancel out, and that's it. And well, we have a lambda here, right here. So we would get lambda S E V N. So it is extensive, so that's good. And what else? Well, let's check that the argument of the natural log is dimensionless. So the argument of the natural log is dimensions of volume times dimensions of mass, energy over h squared, which is just, well, let's just write h squared, and d halves. So this is just kilograms to the dth power, okay, because the volume, sorry, not dth power, meters. Meters to the dth power, because we are in a d-dimensional space. Kilograms to the d half power. Joules to the d half power. Joules to the dth power, and seconds to the dth power. Just like before, we actually have done this before, but let's do it again. We get 1 over joules to the d half power, and this is just kilograms meters per second squared, times kilograms times meters over second, and all of this raised to the d half power, and this is squared. Okay? So just check it by yourself if you don't trust me, but we get that these two cancel out, and the argument is dimensional. So far everything about our entropy makes sense. So that's good, I think. Now, what else? We can compute the pressure. So the pressure is given by the temperature times the partial derivative of S, expressed in terms of EVN, as we have it here, with respect to V. So we have this times the partial derivative with respect to V. And we can actually do this real fast. This kV comes out. It means temperature times Boltzmann constant times N, and well, the partial derivative with respect to V of these two cancel out. And the natural log, as always, you can do this kind of this trick, which is all the terms here times V, and if we take the partial derivative with respect to V, we get that this is just all of this V, the partial derivative of all of this with respect to V, which is just these terms, and we get 1 over V. So this is a really fast way of doing it, and this would be our pressure. If you notice, this is in fact the equation of a state of an ideal gas. This is the same expression that we got with the ultra-relativistic particles, I think, if I remember correctly. So as you see, they have the same equation of state. So what? We can write it as PV equals Boltzmann constant, this is a V, times the number of particles times the temperature. Now, we can do the same for to find the temperature, which is defined by 1 over T, is the partial derivative of S with respect to E expressed in terms of V and E as we have it here. So just taking the partial derivative with respect to X. We'll do the same trick. KV and N come out of the derivative, and here we have the natural log of something times e to the d half power. If we take the partial derivative with respect to e, we get this something times d halves e to the d halves minus 1, and this something which cancel out times e d halves, and this is what we have d over 2, and this is just 1 over e. So this would be our temperature. Our temperature is given by this, and we can put it here as 1 over the temperature is kVd n over 2e. Now, well, of course you can check the dimensionality of the pressure and the temperature. but here you just get that Boltzmann constant is joules per Kelvin, and energy is Kelvin. Sorry, is joules. So joules per Kelvin over joules is just 1 over Kelvin, which is our the exact dimensions of 1 over T. What else? Well, we can compute the specific heat capacity at constant volume, but in order to do this, we have to express T, let me just put it like this, S in terms of Vn and T. So we have to express in terms of V, T, N. So, how do we do this? Well, it's actually not too hard. We know that E, so V, T, N, so we already have it expressed in terms of V and N, but we don't have a T, so we can just substitute the E by our T. So the entropy in terms of V, T, and N is just Boltzmann constant times N times the natural log of Vn, and here we just have 4 pi m over dn h squared d over 2, and here I'm gonna separate it because instead of E we have this expression, and well, from here we have that E is just kv dn over 2 times t, so we can write it as kv n d over 2 raised to d half power times t to the d half power plus 1 plus d over 2. Okay, so this is our new expression for the entropy in terms of volume, temperature, and number of particles. And as you notice, it's just the same. It's exactly the same. We have this t, and here we just take the derivative with respect to t. But it's just the natural log of something times t to the d half power. So if we take the partial derivative with respect to t, we get d halves, t d halves minus 1 over t d halves. This is just d over 2t. Okay? So we have our kvn, so we get kvn and d over 2t. So this is just kvn d over 2. kvdn over 2. Let me just check it. Yeah, I think it's correct. So it is just Boltzmann constant times number of particles times d over 2. Okay, so finally we can also calculate the heat capacity at constant pressure, and it's given by this expression right here. And we have to express the entropy in terms of temperature, pressure, and number of particles. So we already have it in terms of number of particles and temperature, but we have it in terms of volume instead of pressure. So we need to find a relation between the volume and pressure. And we have it right here. It is the equation of state. So instead of volume, we will write kv nt over p, but n and n cancel out, so I can just express this as kv t over n. And well, this t can go with the other one, and here we just have a plus 1, and that's it. So our heat capacity at constant pressure is the temperature times the partial derivative with respect to temperature of S at constant pressure and number of particles. So this would be T times kV n, and the partial derivative of the inertial log again. So we have something times Td halves plus 1 and something times Td halves plus 1. But we have to take the derivative of this term. So we have d halves plus 1 and t to the d halves. And this is, well, this t can go up here, and these two t's cancel out. This one cancels with this one, and we get that heat capacity at constant pressure is given by d halves plus 1 times Boltzmann constant and number of particles. So let's just put it here and let's do one last thing. So we have this is KV. Let's check. Yes, this is KV and D halves plus 1. So yes, and if we compute now the ratio between the capacities, we get a very well-known result, which is the heat capacity between the heat capacity ratio of a monoatomic ideal gas. We have been dealing with a monoatomic ideal gas. The only difference is that we have generalized it to d dimensions. Okay, so we are working with a abstract d-dimensional space. So our gamma is Cp over Cv, and if we divide Cp by Cv, we get d halves plus 1 over d halves, and we can rewrite this as, well, if we multiply everything by 2, you get d plus 2 over d. This would be the expression for the heat capacity ratio of a monoatomic ideal gas in d dimensions. If we compute it for d equals 3, which is the regular everyday case, we get 5 over 3, which is the expected result. If you look at my channel, you'll find another video in which we do this, the same problem, but for a relativistic gas. A gas in which the particles move with relativistic speeds. And in that case, instead of 5 over 3, we get a heat capacity ratio of 4/3. So by adding this ultra-relativistic speed, this ratio becomes a bit smaller. And well, yeah, I think that's everything for today. So I hope you liked the video, and well, see you in the next video.